My name is Tim Miller, and for a number of years I was at the Applied Research Lab at Penn State. I did a lot of work there on power energy systems for underwater vehicles. And this is a type of underwater vehicle that's kind of different than the one I had worked a lot on, but that I was kind of interested in doing. And I thought it would be apropos because these types of systems, these underwater gliders, are heavily used in the research community and in the sensing community and the scientific community, one. And second, the ones that we'll eventually get into toward the end of my talk actually harvest energy from the environment. That allows them to enhance, increase their range, and to do other things that are kind of interesting. So, I want to acknowledge a couple people here. A lot of this work was undertaken under the sponsorship of Maria Medeiros at ONR. She was running a program called the University Laboratory Initiative at one time. That was really kind of a neat program because what it would do is during the summer I would get a graduate student from some other school, in this case Brunswick, and they would spend their summers with me. And then during the rest of the year they would be up doing their graduate work with their advisor, in this case Warren Gandhi, who was an old friend of mine who was up there. And so Maria supported this, supported Alex for 3 years. In fact, he's getting his PhD in August. And Warren was gracious enough to let me be his external outside committee member. So I've been associated with this at various levels for quite some time. And what we're going to be talking about are autonomous underwater vehicles of a specific kind, of gliders. And this gives you a picture of 3 types of gliders: the spray glider, the Slocum glider. Slocum was an early explorer and naturalist, ocean naturalist, and then the sea glider. And one of the first ones was actually this one, the Slocum, and it was developed by Webb Research Corporation. Webb is still alive, and he's still very active in all of this thing. But basically, you take a look at these things. They're basically bodies with wings on them. Wings aren't very big because, well, you're going through water, and water's 1,000 times denser than air. So you can do some things that you can't do in air. But one of the interesting things about them, both that has kind of really made them interesting to people, but at the same time made it frustrating because sometimes it conveys a false impression or a false view, are pictures like this. This is the Scarlet Knight. This was a Slocum type glider that was worked on by some students at Rutgers. And they launched it off the Jersey Shore, and 221 days later they recovered it off of Spain. So it went along for quite some time. This is the path that it took, and it covered a distance of 4,600 miles. It expended 8 kilowatt hours. Okay, that's a measure of energy. So think of something that uses 8 kilowatts, and you run it for an hour. Or in other words, you run something that has 11 horsepower. You maybe run a couple of lawnmowers for an hour. That's the amount of energy. That doesn't seem like very much, and it isn't very much that they use to traverse this. Now, where the key thing to keep in mind are a couple of facts here, and they're not bad things, but just keep in mind. The average oversea speed was 0.9 knots, just over 1 mile an hour. So it didn't go very fast, and that is a big key. And another thing that's interesting is that in the 4,600 miles it went from point A to point B, it had 1,400 miles of vertical traverse because it's a glider and it works by gliding down and ascending and gliding and ascending. Now this is where some of the misconceptions come, because people look at that and say, oh, it's gliding, it's climbing, it can run forever because it's harvesting energy from the gravitational. And that's not how it works. What really helps this a lot is that it's slow. Whenever you have something slow in the water, you get long endurance because the drag is so low. Drag goes up. Drag force goes up with the velocity squared. But we know, my dynamics students all know, that the power is the force times the velocity, so the power required goes up by velocity q. So if you have it going really slow, you don't need much power. So anyway, keep this 1,400-mile vertical transverse in mind. We'll get back to it in a minute. And the way that this thing works, the way that it's able to transverse up and down is through use of something called a buoyancy engine. And this is just a really clever, beautiful little thing that came out. It's one of these things you look at and say, boy, I sure wish I would have thought about that because it's so sweet. Okay, so this is one of the sea spray gliders. But the basic idea here is that you have a pressure hull. That's this thing here, this part down here. And that's dry. You keep all your stuff in there that you don't want to get wet. And in there you have your battery pack, and you have a high pressure pump. And you have, you can't really see it here, but you have an internal bladder or internal reservoir in which you store oil. Oil is less dense than water. Okay. Well, then on the outside of the pressure hull, but inside of this little fairing here, so you have good hydrodynamics, is a bladder. And so this is what we call a flooded section. So that the stuff back here is actually at the pressure, whatever the outside pressure is. So if you're at 1,000 meters depth, it's the pressure that's at 1,000 meters. And you have a bladder there. And so the way this thing works is that if this bladder is not full of oil, okay, so all the oil is inside of here, this is all water, and this is designed to be slightly heavy in water, slightly negatively buoyant, just a little bit. And so it descends, and it's got wings, and so it descends and has a glide path. When you get to where you want to come back up, you have this high pressure pump in there, and the pump then pumps oil from the internal reservoir out and starts to displace some of the water in the back here. So it's lighter. The displacement is lighter, the displacement of the water is less. Okay, well this is more, and it's displaced by oil. And so that makes it a little bit less dense than water, and so it wants to rise. And again, it has fins and it rises at an angle. And so it kind of goes through that type of sawtooth pattern. I want to identify some things. And what's interesting is this thing here, this is an antenna. It sticks out the back. So the way this thing works, if we were to go back to the original picture, I had a better picture earlier. But when it comes to the top, when it comes to the surface, it actually pitches forward. I'll talk about that in a second, how it does that. And it sticks its antenna up in the air. And then it broadcasts its information. It broadcasts you where it is, broadcasts you whatever it is that it was measuring and going from here to here to here and along. And it broadcasts that out, that information. So, again, this is it here. This is the battery. Look at this battery. It takes up a lot of volume. And the thing is, this thing has to have some empty volume because it has to be essentially neutrally buoyant. 1 kilogram per meter cubed. All right. If it's too heavy, it's going to sink, and it's not going to have much range because it's whatever the depth of the ocean is, that's the range. So you have a battery in here, and one of the clever things they did is they have the battery in this system actually located on this rail. And if they wanted to pitch forward, then they move the battery pack forward a little bit and pitches it down. If they want to pitch it up, they move the battery pack a little bit back, and that pitches it up. And so that's how they control pitch. They can also control the roll of the vehicle in a similar manner. They may have additional batteries that can rotate a little bit to change the roll attitude of the vehicle. So it pitches up and pitches down. Now, all these things, these take energy, right? So the pump requires energy from the battery. The trim conditions require energy from the battery. What's typically called the hotel load, or the communications, or the sensors, all require energy as well. So these are all energy draws that are drawn off the battery. So one of the things I talked about how was the speed is very low, but the other thing that with these types of systems is they're also designed to, they typically use primary batteries that give them a lot of energy that they replace at the end of the mission. These aren't very big vehicles, so the batteries aren't that expensive, there aren't that many. But it allows them, though, to do with something like this, and you got I don't know if you got an idea of how big it is. This is, well, here it is, 1.8 meters long. Less than a third of a meter, about a third of a meter in diameter. They aren't very big, but they can go a long ways. Okay, until they get to the point where the batteries run out. So let's keep going a little bit with that. And oh, here we go. So I'm going to have equations on here, and I'm talking about energy in my dynamics class as well. And my students are really probably admitted me because I'm talking about a lot of things. But let's talk about the energy of this thing. So you've had the basic energy, I think, in your physics class. Work, basic form of work is PdV, right? Pressure times change in volume. PdV, classic expression. Okay. One ways further. Well, with this type of system, the change in volume we're talking about is related to the volume times the density of seawater times gravity. So it's the mass, or the weight, that is the weight of seawater that you're displacing. That gives you a buoyant force. Now this is a little picture. This is distance over ground, or distance over ocean surface, or however you want to look at it. But this is like the level distance, and then this is the glider going down, the glider going up. Brother Marius has never seen anything at all like this picture before in his life. For those of you who used to be a glider pilot, or he is a glider pilot, so. Okay. And so we can start throwing some things in there. So here's the change in volume that we're talking about. The pressure that you're acting against is the density of the seawater times gravity times the depth that you're under the water. It's called a hydrostatic pressure. And so from that, you can get a relatively simple expression for the amount of work you need to do in order to make this thing go through a cycle. So this is just another picture showing buoyant force. In aerodynamics, this would be the weight of the vehicle. In hydrodynamics, it's the weight of the vehicle minus the weight of displaced water. Okay, for wet weight. It's a little bit different. And you can do some things here about the angle and the relationship between lift and drag. And the important thing that comes out of this is that the work is equal to the drag force. And if you brought this over, it would be over the distance you travel. So work is equal to force times distance. But there's nothing in here that talks about the way the drag was incurred, right? This thing is going up and down, but we're looking at it over this distance here. This could have been just pushed by a propeller, that distance. So basically, the point of this is to a first idealized approximation, the horizontal range of a glider is equal to the horizontal range of a conventional underwater vehicle with a propulsor. That seems extraordinary because these things go 4,000 miles or something. Or they go 4,000 miles at 1 knot. Okay. Now, so let's go further with that. Because I'm going to kind of lay it out like, oh, why are you looking at gliders? And then I'm going to point out why you want to use gliders. Okay. So if you go the next step, one more step past that, is you start considering efficiency. So there's two main efficiencies to deal with. With a conventional autonomous vehicle, you have a propulsor efficiency. They're typically around 80% or so. Okay. And that is, how well does the energy or the power from your shaft that's rotating get conveyed to the water. That's the efficiency. And there's another efficiency that's important. It's the pump efficiency. It's the efficiency of the high pressure pump, which actually surprisingly tends to be fairly low. But even if it's high, even if it's a high efficiency, you can end up with these curves here that suggest the angles that you have to glide at in order to make the glider more efficient than a conventionally powered system. And what you start to find out is you have to have these things kind of glide at a pretty steep angle in order for the efficiency to be there. And even then, if your propulsor efficiency is much above 0.5, and it almost always is, you're always going to be in a place where at these lower speeds we're talking about, it makes more sense to go horizontally with a conventionally powered rotating propulsor. But the thing is, if you're doing scientific research, if you're doing battle space preparation, if you're doing things like going in and you want to measure, I should have been smarter the way I did this, but if you want to measure things like salinity or temperature or chemical composition, you want to do it over a volume of water, right? You just don't want to go over here because you don't know what's going on down here. Okay. So what the gliders give you is for a given distance, you're covering a lot of volume, and that's what's really nice about it. You cover a huge amount of volume, and you still cover a good distance because you're okay with going at a knot or 2 knots. We'll go all the way through. And, oops, see, I'm going to talk about whales in a second. So yeah, this is what I just said. There are these gliders, and these gliders can move through distance, okay, across the Atlantic. But there are currently, as of 2016, there are 3,000, they were 3,000, April 2016, there are 3,829 of these Argo or Argus floats throughout the oceans of the world. Look at that. And they know where they work because when they come to the surface, they tell where they are. Right? And the colors go by, the colors go by basically what countries have them out. And the way these guys work is you dump them overboard in a location, and they have a battery, and they have a computer, they have an antenna, and they have their sensors. They have a battery, and they have a little motor in here, and a piston that fills or allows to have unfilled a little bladder, the same kind of thing. So if the bladder is unfilled, goes up, the oil, whatever goes up, it gets heavy, it sinks, and then they run this little gear motor, okay, and that drives this piston, and it causes the hydraulic fluid or the oil to fill up this boot, makes it lighter with respect to the water, and it goes up. It goes up, down, up, down, up, down, down. Now, one of the disadvantages, one of these things, this is really extraordinary. Look at all of these that have been out there, that are out there, constantly monitoring the ocean. That's really cool. One of the problems is, of course, they tend to accumulate in central locations because of the way the currents work. I imagine a lot of them probably end up here with the plastics, right? In the gyre. And so they know where they are. Sometimes they'll go out and they'll pick them up and take them. I was commenting that stuff like this is actually considered to be salvage. And so if you pick it up, arguably it's yours. Now, the people that own it, if they come there like 30 minutes later and you have it, they may not consider that to be a valid claim. And this is particularly true if it's two countries that might not like each other very much. So the next step then, so now we're talking here about this oil, moving it up and down. And we get to a concept called bioinspiration. And I like to use bioinspiration rather than biomimetics. Biomimetics is saying, in my view, is saying that the way that an animal does something, the reason why an animal does something is because it's conserving energy by doing it. And sure enough, it could be conserving energy by doing that. I just don't know if that's the reason why it's doing it. But, however, I can look at that animal and I can be inspired by it to do something. And so this is really an interesting idea, like you'll see in a second. Buoyancy control is a function of the spermaceti organ in the sperm whale. So this is the biology of the thing. Sperm whales are nearly hunted to extinction because of the oil in the front of their heads. And people have been speculating why they had that oil. And part of it, I think, is the sensing, right? The way that it conveys the acoustic signals back. But they found something interesting. And what they found was that as blood flowed into that organ and warmed it up, the density of that oil goes down. On the other hand, it could be possible, they proposed that maybe to go up, this density go up. To help them go down, maybe they can bring in water through their blowhole to cool off the oil, make it denser so they can go down. So they can go up and maybe they can go down. Well, so they did some calculations, and some of this is kind of morbid in that what they do is they go and they find dead sperm whales washed up on the shore, and they make measurements and stuff like that. And on the basis of that, they inferred a couple of things, that by doing so, they can incur or produce basically this amount of lift and this much amount of sink. So you can have some degree, now, whales are heavy. Well, whales are heavy. But the baseline weight of a whale in water isn't very heavy. They're nearly neutrally buoyant because they displace an amount of water equal to the weight. So just a little bit of weight like this, or lift, kilograms, this should be kilograms of force, I'm sure, is enough to actually help them maintain level action or go up or down. Is that why they do it? Don't know. However, somebody said, that's kind of a clever idea. What if we design dive a robot with whale-like buoyancy mechanisms? And so what they have here is they have a little oil up here, water here, and this is vented. This is seawater, so this is vented down to the ocean. And a little heater, okay? So when they heat up the oil, it expands, the water's forced out, okay? It becomes less dense. It rises. Okay, they get to the point where now what they want to do is they want to cool off the system. They let the system cool off. You turn off the heater. The water and the oil cool it. Oil cools down. It contracts. Water fills it up, and now it's heavier. And now you can go up and down, up and down. And again, you need energy to run that heater. And this is just kind of a picture of that going up and down, and they tested it. Well, question, can we exploit underwater thermoclines? I'm asking that, but the answer is yes, otherwise I wouldn't be here, right? So yeah, you can. Okay, so if you go along the near equatorial type of locations, you can see a relatively large, I should say, difference in temperature at the surface of the water, ocean, and relative to deep depth. This is 2,000 meters, this is 1,000 meters. But right in here, there is a pretty substantial gradient, all the way from about 25 degrees C or so, all the way down to even 0 degrees C. The water at the very bottom of some of the ocean is actually less than 0 degrees centigrade. It's salt water, so it will freeze. And it's at high pressure. I mean, it's a little different. So we talked about how buoyancy change controls climb and glide, how the traditional gliders use these high pressure pumps. In this case, we're trying to look at, when people are looking at thermal gliders linked to the temperature of the ocean to modify the buoyancy of the autonomous underwater vehicle. And the Slocum glider was the first one to do it. Slocum Thermo used wax that melted at within this temperature range. And wax not a heck of a lot different than the wax or the waxy substance that the sperm whales have. Basically, they created a mechanically negative coefficient of thermal expansion. Normally, your coefficient of thermal expansion is positive. And so I'm going to run through this, how it works. So basically, you have your pressure hull at slightly less than atmospheric pressure. And inside you have wax that melts at a relatively low temperature, around 24, 20 degrees C. This is your oil. You have check valves. These are one-way valves. You have a three-way valve here. This is flooded, so this is the bladder. It's still that bladder. It's at the external pressure. And at the surface, before anything's going on, this is at relatively high pressure. So, at the surface, the hotter, the warmer surface water heats the wax and melts it. And as it melts it, it expands, right? It's a solid becoming liquid, it expands. The expanding fluid pushes the oil, this is still closed, pushes the oil around, and it goes into this little tank that has some nitrogen in it, and it pressurizes the nitrogen. So that's a way of storing the energy in the form of pressurized nitrogen. So, displaces oil, the oil pressurizes the nitrogen. So it's still at the surface. So after a brief time at the surface, you open your three-way valve. This is at pressure, it's not at pressure. This is at a lower pressure, and so the higher pressure oil flows into this inside of the vehicle, okay? This is now displaced by water. The density, effective density increases, and the vehicle sinks. When you get to the depth that you're interested in, or at depth, the heat is rejected to the low temperature water. The low temperature water is cooling the wax. It's freezing the wax. The wax volume is reduced, okay? The wax volume is reduced. And what happens is then the oil starts to flow from this guy here, through here, and starts to accumulate back where your working fluid was, okay? But then you close things up and you have all this pressurized nitrogen. And that pressurized nitrogen then forces this oil that wasn't there before, forces it now down into this thing. Fills up the bladder with oil, displaces the water, makes it less dense, the vehicle rises. And then the cycle keeps going up and down. It's a real plumber's nightmare. It's amazing that somebody came up with it, but it actually does work. So this is just kind of a picture of a Slocum glider with a buoyancy engine of that type retrofitted to the back. Okay, well, so what I want to talk about is some work that I've done with Alex and with Farham about using shape memory alloys instead to exploit underwater thermoclines. So this is just a different picture of the same thing we showed before. This is the difference in water temperature from the surface to deep down. Okay. Shape memory alloys. Okay, real quick lesson here. Okay. Alloys. Okay, let's just talk about steel. Okay, you're making a sword. Doing who watches Forged in Fire? You can be proud to watch Forged in Fire, so go ahead and raise your hand. Thank you. At least one person does. Thank you. Forged in Fire, you make a sword and you quench it. And what happens when you quench it is metals and other alloys go through these phases. And alloys, remember, are metals with other things in them to give them properties. So iron and carbon, for example. And at higher temperature, the form that the iron and carbon takes is of a form that is more compact and harder. And then when it's cooled off gradually, it forms a different phase of alloy called martensite, which is softer, more ductile, and is more expanded. Now this happens if you cool it nicely or you heat it nicely. If you quench it, that is, you put it into water or oil really quickly and it cools very rapidly, then what happens is this form is frozen even at these lower temperatures. It maintains this form. Okay? And that's why you quench a sword or you quench something that gives it harder surface on the outside, more brittle but harder. It's just basic. But you can do that with other things. For example, you can do that with an alloy called nitinol, which is an alloy of, I'll show it to you right now, nickel and titanium. In 1947, somebody discovered that you could do that, and they created what they call the shape memory effect. That is, it formed one way and it deformed the object, and then when it cooled off, it returned to its regular form, and when you heated it, it returned to that, and so you could actually have a structure that would change shape. And what's interesting with this nitinol is that it's a solid state phase transformation. So water to steam is a liquid to vapor phase transformation. This is a solid to solid phase transformation that's taking place. There are some transformation temperatures, and it goes between this austenite phase and martensite phase. And it does so over a range. So the transformation starts at a temperature and it ends at a temperature, and likewise it starts going back the other way. It starts at a temperature and it ends at a temperature. And oh, by the way, the temperature that it starts and ends going to austenite and the temperature that it starts going to martensite are different temperatures. That's called hysteresis. But whenever you get these you can draw these kind of pictures of stresses and things like that, you can start getting these little polygons in there. It gives you an idea that maybe there's some useful work or something that can get extracted from here. Okay? And indeed, what we're talking about is, can we design a system whereby at the warmer, higher temperature near the surface of the ocean, for example, we have a wire or a spring or a structure that causes the buoyancy to decrease, that it shrinks. And then when it goes down below, it recovers and it spreads and then it rises. So the idea here is that this would be, our idea was this would be more of a passive system. You wouldn't have to have a bunch of valves going all the time. And in fact, perhaps you could even build it into the whole of the vehicle. And in fact, if you think about it, by training, I'm a mechanical engineer, so I love heat engines, right? This is a classic heat engine. Okay, you're adding heat. Okay, it goes down to a volume change. It does work. We talked about the work, PdV, and it rejects heat at the bottom of the ocean. Heat in, do work, reject heat. It's a classic heat engine. Okay, that's what we have here. We have a heat engine that's extracting heat. Now, the efficiency is really lousy, right? Carnot efficiency is 1 minus the rejection temperature over the addition temperature. And that delta T is only 25 degrees C, so it's lousy efficiency. But the ocean has tons and tons and tons and tons and tons of energy. So if you can use it, why not? And I just showed it, okay? There we go. And so this is an analysis that we did with a typical one. And again, what's showing is kind of the same thing except for the temperature. But here we have stress, and here we have strain. And from your thermodynamics class, I don't know if you remember having a diagram that was a PV diagram. And the area that that the cycle made in the PV diagram was the work. Well, stress basically is like a pressure, and dV is like a strain. You're changing the dimension. So this area basically is a reflection of the amount of work you can do, or the amount of work that you've done on your shape memory alloy. that might be available over this modest temperature range available to use. Oops, I pushed the wrong thing. So what are factors? Well, we were looking at making a design of this thing. And so your vehicle itself affects your engine, your shape, memory, alloy, buoyancy, heat engine. We couldn't come up with a better acronym. The vehicle has a drag coefficient, has a mass associated with it, a wet weight, dry weight, depending upon how buoyant it is. There are environmental concerns, thermocline, the size of the thermocline, density of the water, which can be different in different parts of the world. The alloy itself you're using is different transformation temperatures. The thing about nitinol is you can tune it to transform at different temperatures by varying the amount of titanium and the amount of nickel. So you can get quite a range of recovery. And so this is kind of the ideal here. We had this thing, basically you go down, you hit this bottom region here where you start a transformation, you finish it here, it stops, rises up again, starts, stops, and then you're going up and down, up and down, up and down. That's the general ideal. And so we developed a kind of a simplified model. This is the force exerted due to gravity. Okay. This is the acceleration of our vehicle. This is hydrodynamic drag that we have here. And this is a volume change effect that is actually very strongly related to the gravity effect, but has to do with the change in wetted volume of the vehicle. So the change in the strain or the length of our sheet memory alloys. So you come in, you can add some more equations to close your system. And you can start doing some calculations, and again, these things like you change the temperature, it starts changing over a range of temperatures as stress is accumulated in the wire or dissipated from the wire during heating or during cooling. Nitinol has a tunable range from negative 50 degrees up to 110 degrees. Eventually, this is what we kind of fooled around with. Eventually, I think we would want to go to this copper zinc type of shape memory alloy. It has a little bit better characteristics. But again, we're trying to go through this type of shape. You can see small hysteresis, large hysteresis. This is a large gap between transformation. And this is kind of what happens here. This is the depth of our vehicle. These are simulations right now, okay? Depth of our vehicle down to 750 meters. And we're using the thermocline I showed, right? The one that you put kind of like that. Okay, we put it that as the water temperature. This is the speed of the vehicle. So initially it's going, it maxes out at about 0.4 meters per second. Starts to slow down as it goes through its transition. Then it transitions and starts to go up at a slower speed. And then back up, down, up, down, up, down. And these are locations on our stress, our temperature strain curve. This initial thing is off kilter because we started it at a different temperature than the steady state temperature. We started it at a temperature in the atmosphere. But this is kind of the way it behaves. It goes up with this type of velocity profile through this type of depth dependence. And just another similar picture, but small hysteresis, large hysteresis, kind of the same type of behavior. It goes up and down in different amounts depending upon the alloy type. And this gets to what I was talking about before. If you then plot the stress versus strain, you end up with a curve of pressure energy that the shape memory alloy is storing. So this is energy that's available to drive the machine, the device. Okay. So we came up with this thing. We scaled it to ocean operation over a 770 millimeter depth. We demonstrated numerically that we think it would work pretty well. We compared it to the Slocum glider. We can go pretty deep. We cannot come to the surface because of that transition thing that we're going through. Our maximum velocity was about the same. The period to go through this is about 1.5 to 1 hours, go up and down. We looked at things like fatigue life, because these are wires getting bigger and smaller, how long they will last. So now the next step is we wanted to make one. And so this was part of what Alex did during the summers working with me, is he put together this cylinder arrangement with a spring in here and then 4 shape memory alloy wires. And then this is testing of the machine initially. You may notice that we're going to relatively, we're going all the way up to almost to 75 to 80 degrees centigrade. That's simply because we didn't want to, it just was going to be a hassle to get the alloy in the range we wanted. And we were able to accommodate this. This is still liquid water, so we just tested the device. But anyway, this is predictions. This is what we measured for our stroke position versus temperature. And in fact, this is just an example of one run. I'm going to run a little movie. And to test it on the bench top, we actually joule heated the wires. So we ran a current through and heated the wires. And this is kind of nice because what it means is that if you don't have enough delta T from your ocean, well, maybe you can just run some current through the wires so you can still actually what they can make for. Okay, this is really kind of a little boring, but I'll try to.
Yep, August 1st, 2014, this is the dry test.
I'll tell you what, let me turn the volume down first. I didn't realize it was so high. There we go.
Yep, August 1st, 2014, this is the dry test.
Okay, and hang on, we need to go. What I want you to see is the problem I'm running into is let's see if this works. Okay, first of all, look at this. I want you to watch this. And so I'm going to fast forward to 1 minute, and then you'll start to see it move this way. So the thing's contracting. And then you're going to see it after 2 minutes, it's going to move the other way, it's expanding. So it's just going to contract and expand. It's not particularly exciting, and hopefully I can do that.
Yep, August 1st, 2014. Dry test with
I'm trying to get the thing up. Get it, and you just have to try it this way.
Yep, August 1st, 2014.
Okay, it's a little bit harder to see, it's not quite so big, but you can see it here. At 1 minute, this will start to move. This is all shear. We get to move ahead to a minute. See how it's moving? Yes? No? Good. It's moving. It really is.
3/8 of an inch.
Okay. Then I'm going to move ahead to 2 minutes. Hopefully. It'll start going back. starting to move now back. So it actually goes back and forth, really slow, like watching grass grow, but it does. And so the next step we took was to try to test it in water. So this is Alex, by the way. And this is the test site out of the Flood Research Lab at Penn State. And so what we did is basically we had warmer water up here, and we put a lot of ice water down here, and we put the thing in here, and what we tried to do is see if we could demonstrate it going up and down. And we did, but it didn't quite work as well as we wanted to, but it did work. And it's hard to see here. If you come to my screen, you'll actually see it much better. The photograph just didn't come out very nicely. But you can see this thing here. This is the scale on the piston. Okay. And if you look at depth, if you look at my screen, you can see that it goes to here. So it actually moves as you go from the higher temperature up above to the 0 degree temperature below. And so I can calculate, it was a displacement of about a 1/4 inch. So I can calculate a change in volume of about 13 milliliters. So the amount of work that was done by these 4 wires is 0.2 joules. Not a huge amount of work, not a huge amount of energy, but not so bad for a first-time demonstration of a concept. So we were kind of excited about that. So what is the next generation? And I'm almost done here. So this is what we have now. Started test, room temperature, heated it to 100, heat the wires to 190 degrees, return to room temperature, went back and forth. A clunky looking piston. Well, what if we did something to get back to the bio-inspiration source? I mean, could we have a vehicle that's like this puffer fish in which the outside shell, if you will, of the vehicle, of the fish, is able to change shape and change volume by doing work? Interesting question. Can you do it? Well, there are things like these manufactured truss systems that you can make that are called aesthetic cylinders. That is, these are cylinders that have a negative Poisson ratio. Rather than having it push in and bulge out, things with negative Poisson ratios push in, they bulge in. Now this one's constructed, but there are natural ones. The cork in your wine bottle is aesthetic. That's why you can get it in. Push on it, it goes in, try to pull on it, it doesn't want to come out. That's because pulling it actually makes it wider, it's aesthetic. So the question is, the open question I have is, could you manufacture something like this out of shape membrane alloys? And then you start having your shell of your vehicle not only functions as a shell, but also functions as an engine. It's multi-use. And the last thing that Alex is doing, Alex is investigating this, and this is part of his PhD work as well. Well, why don't we not bite off more than we can chew? Let's just worry about the airfoils. And what if we just design airfoils that change their camber, their shape, in response to warmer surface and colder depth temperature, instead of having to move our batteries back and forth and we take energy that way. And so we're looking at that as well. Or Alex is. This is Alex's PhD. So thank you, and any questions I'd be happy